Well, you came back to learn more, and that's great. In this video, we are just going to talk about binary shift, okay, in data chapter of IGCSE Computer Science, okay. So shift, okay, simply it means moving the bits to the left or to the right, very simply, okay. So introduction to binary shifts. What is a binary shift? A binary shift involves shifting all the bits in a register, typically an 8-bit pattern at IGCSE level, okay. But in computer, we can have just 16 bits, 32 bits or things, okay. So I specified number of places to the left or to the right. Mathematical equivalence, a binary shift is the architectural equivalence of shifting binary digits to by power of 10, okay. So when you're just kind of moving the digits 1 unit to the left, so everything multiplies to 10, okay. If you just move them to the right, everything divides by 10, okay, is divided by 10. So we just have that. See the need for speed, why processors use shift, okay. So standard arithmetic logic like addition just takes a lot of time. So wherever it can be done, we would just simply perform shiftings to just instead of multiplication. So the standard arithmetic logic requires complex circuitry and multiple processor cycles. And with binary shifts, yeah, only with moving bits to the left or to the right, we can just perform kind of some big operations. So that's why we are just using that, okay. So processors use shifts as a highly efficient shortcut to multiply and divide by powers of 2. Multiplication and division by 2, by 4, by 8, by 16, they can be just done very easily with shifts. And we have gotten two types of shifts, okay, logical shifts and arithmetic shifts. We will just study about them individually, and we will just see how different they are, okay. So first of all, yeah, logical shift. So we will just study about logical shift left and logical shift right. First, logical shift left for unsigned multiplication. See here, these logical shifts are used for unsigned multiplications, okay. And how does it work? Move bits in places left, then after that discard the leftmost bits, the ones that just get out of the register size, okay, and fill empty spaces on the right with zeros. So see, let's just perform 2-bit logical shift on this. So how do we just do that? The first one, yeah, just 2 bits to the left, it just shifted, okay. Then the next one, 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 and see here the 2 last one, because we just moved 2 places to the left, the 2 last ones are discarded. We do not have any space to store them, okay. And in logical shift, what do we do with the empty spaces? We just simply fill them with zeros. Got it? So see here, this is binary 20, 16 plus 4, so that is 20. And we just moved 2 bits to the left. Now what is that, okay? This is 64, okay? 64 plus 16, that is 80. So simple. We have just done a multiplication, okay. 20 multiplied by 2 to the power of 2. 2 units we just shifted, yeah. So 2 to the power of 2 will be 4. So 20 multiplied by 4 will be 80. So as you can see, 1 bit shift to the left is multiplication by 2 to the power of 1. 2 bits shift, that is multiplication by 2 to the power of 2. 3 shifts, that will be this 2 to the power of 3. So we will just simply have that, okay. As you can see, we can use shifts to perform multiplications to any power of 2, okay, 2 to the power of 1, power of 2, power of 3, whatever. So I hope you have understood this. Once again, just do them on your paper with yourselves, okay, because you will have to just do them on paper in the exam. Then logical shift right, okay. Logical shift right is just kind of the same thing, only this time we are just moving to the right, okay. Move bits in places right, discard rightmost bits, okay, the ones that get out of the register size. Fill empty spaces on the left with zeros. So see here, this is just what we have, that is 20, okay, denary 20. We want to just move it 2 units to the right. So the first one, okay, the next one, the next one, the next one, moved. So till here, yeah, we just moved everything 2 units to the right. Now this 2 will be discarded, okay, because that will be just that will go outside the register. And the empty spaces in logical shifts, we have to just fill them with zeros, okay. In logical, we have to fill them with zeros, so that will be 0 and 0. So see here, that is 16 plus 4, 20. Here that is 4 plus 1, 5. 20 divided by 2 to the power of 2, okay. 20 divided by 2 to the power of 2 is equal to 5. Clear? So that is just our denary 5. So the right shift performs division. Clear? So what about the signed complications? Okay, here logical shifts can be just used for unsigned divisions or unsigned integers. Okay, what about for signed ones? Okay, so if we just perform this with the logical shifts, if we have gotten one here and that is just our sign bit, moving that to the left will just kind of, that is just not a part of number, but here we are just adding things here. Okay, so it does not work with that, because the MSB in signed integers is just simply what it is, not a number, it's not a part of the number, it's just simply the sign. Okay, so in 2's complement, what do we do? Okay, so fatal error, filling the left with zeros, as we just told you before. Okay, filling the left with zeros accidentally changed the sign from negative to positive. So if we have gotten this negative in logical operator, we just told you that yeah, if you just move them to the right, then fill the empty spaces with 0. So if I add a 0 here, the sign will change, and that is just not correct. Okay, negative 20 divided by 2 will be negative 10. It won't be positive 10. Okay, so logical shifts break signed integers, so a special mechanical rule is required. Let's see what do we do, or what can we do for this. So in arithmetic shift right, okay, which is used for sign division, what we do is just move bits n places to right, discard rightmost bits which are just which fell out of the register, and fill empty spaces with the sign bit value, whatever was just here. Okay, if it was just 1, so you will just simply write there 1. If it was just 0, you will just fill everything with 0. Okay, so as you can see here, we have just gotten this denary value, which is just negative 68. Okay, and we want to just move it 2 units to the right. So as you can see, we are just doing them one by one. And the rightmost bits are discarded, okay, that fall out of the register. Then yeah, the empty bits are just filled with whatever we have in the sign bit. Okay, that is just our sign bit here. So 1 and 1. If it was 0, then it would be 0 and 0. And this whatever we have here, okay, that is just result of a division, okay, in 2's complement. This is also 2's complement. Okay, so you can just simply change that to denary. You will just see that yeah, this will become negative 17. Okay, so negative 68 divided by 2 to the power of 2 units we have just, or two bits we have moved to the right. So yeah, we will just simply have negative 17. Okay, that's it. So arithmetic shift left, which is just used for sign multiplication, is the same like logical shift left. Okay, where we just simply move the bits n bits to the left, then the leftmost are just discarded, and the other thing that yeah we have gotten is fill the empty spaces with zeros. Okay, just remember one thing: in arithmetic shift left, if shifting left changes the sign bit, for example, your sign bit is 0, it changes it to 1, or just 1 to 0. So here be sure that yeah, your math has broken down. Why? Because simply we have faced an overflowed bits. Okay, so we have just gotten to the limit, and outside that limit obviously 8 bits will give us wrong answer. Okay, so for example, here we have gotten 1 and it is 0. So if this 0 comes here, so that 1 is just kind of moved aside, then this completely will just kind of be wrong. Okay, that will be just overflow problem. So the shift matrix, consolidating the rules. So we have gotten two types of shifts, logical and arithmetic. Logical is used for unsigned integers. Arithmetic is used for signed integers. And then we have gotten shift left and shift right. Shift left is just used for multiplication, and shift right is used to do division. Okay, so move left, fill right with zeros, then move right, fill left with zeros. So whatever we have, just do that. Then in arithmetic, yeah, in left, move left, fill rights with zeros, whatever you have. But in arithmetic, right shift, move to the right, fill left with the clones of MSB, or most significant bit. Okay, whatever. If that is 1, so you will just fill the empty spaces with 1. If 0, then just simply with 0. Pause the video, look at this table very carefully and try to understand it, okay, deeply, and just work your examples. Then yet the limit impact on precision. See, if 1 falls out of the register from the right side, okay, what happens is we will just simply use that decimal part. Okay, for example, we have gotten 33 divided by 2, so that is 16.5. But here, because this 1 is discarded, we will just simply have 16. So remember this, okay? The right shift does the integer division, okay, or round down floor division. It does not take the decimal parts, okay. And after that, yeah, the limits overflow risk, okay. On the other hand, just yeah, if shift left remove some ones, okay, so if a 1 is pushed past the maximum limit during a left shift, it cannot fit in the 8-bit register. The result is completely incorrect. This is an overflow problem, okay. So if 1 falls off from the right, we will just simply lose the decimal part, so that is just not very precise answer, okay. But if just 1 falls off the left side, it means yeah, we have just gotten out of the range, okay. So overflow problem. So a 9th and 10th bit are required to store this result, so the hardware limit has been reached. This number cannot be stored inside the computer, okay. Exam practice EDXL style, okay. Give the result of a 3-place logical left shift on the binary number. So read this question, explain why carrying out binary shifts can sometimes cause a loss of data. Pause the video, write the answer for these questions on a piece of paper, then play the video to check if your answers are correct or not. See, so for the first one, 3 shift lefts, so that is 0, 1, 1, 0, and 1. So we have gotten 3 empty places there, and because it's just for logical shift, so we will just put 0 there, okay. And the next one, answer for the next question is, right shifts can cause bits representing fractions or remainders to fall off the right edge. So that is just right shift, and left shifts can cause ones to fall off the left edge, meaning the number becomes too large for the hardware register. So that is just 2 marks there. And final mastery tips, always draw an 8-bit table. Never try to shift bit entirely in your head, okay. Put it on paper. In exam, you have to be very careful, okay. You have to just be precise and make yourself sure that your answer is correct. So do not just do it in your head, okay. Write them down. Physically draw the arrows, okay. Map the physical movements of the bits on your exam paper to prevent counting errors, okay. So draw the lines. You never wrap bits around. Okay, if a bit falls off the edge of the track, it is gone forever. It does not reappear on the other side. Sometimes, for example, one is removed from that side, students just write it on the other side. Okay, that does not happen. If just it is out of the track, simply it is gone forever. And check the shift type. Okay, logical always fills with 0, arithmetic left, anchor, and copy the MSB. Okay, so that's it for shifting. Keep practicing. Wish you all the best. Good luck and goodbye.